Welcome to Math 3000. Hope you guys had a nice weekend. So the plan for this week is to wrap up the material that's going to be on your first midterm exam. So your first exam is a week from Wednesday. So it's March 3rd next week. So it's going to cover everything up to and including what we do this week. So the plan for today is to go over some material from the text. Let's see, chapter 12, I think it is, with functions. And then on Wednesday, we're going to take a look at some disproof and existence theorems. So you'll have a little reading quiz based on that material, and we'll work on that on Wednesday. And then on Monday, we can just, of next week, we can just review, talk about the exam that you'll have on Wednesday. So don't forget, you've got homework due tonight by midnight. The next homework assignment is up. That is not going to be collected next week. Just keep that in mind. We have an exam on Wednesday, so I wouldn't be able to give you guys feedback on that before the exam. So I'll put up solutions and you can check your work against the solutions. But yeah, just because I'm not collecting it doesn't mean that assignment is not important. So definitely treat it just as if you would any other assignment, but you guys can kind of self-grade yourself on those. Any questions before we get started? Everyone's doing okay out there in Zoom land? Okay, well, good. Hope everyone's doing well. Okay, so what you guys read about for today was functions. This is telling me that I am muted. I don't think I'm muted, right? You guys can hear me. Okay. Okay, so yeah, so about functions, domain, codomain, range, things that you're probably somewhat familiar with, but I want to take a look at this in a little bit more formal way. So right, a function is a relation between two sets, A and B. Usually they're real numbers. They don't have to be, they can be sets of anything, where for each input, right, we get a unique output. So we can't have one input going to two outputs, but we certainly can have two different outputs that correspond, excuse me, we could have two different inputs that get sent to the same output. And yeah, so some terminology, we call the domain the set of the inputs. The codomain might be something that's sort of new, right? So this is the set where the range lives inside. So this is where we're mapping to. We might not map to every element in the codomain. So the range is just the set of elements in the codomain that have something mapped to it. So these are pretty similar to what you guys looked at on the quiz. So I'm just going to open up some polling just to see how this is going. But any questions about functions, domain, range, codomain that you had from the quiz? Okay, so
actually, I do have a question.
Yeah.
Can you clarify the difference between the domain and codomain a little bit more?
Yeah, so maybe it'll be a little more clear with some examples. So yeah, so let's first think about whether each of these things are functions, and then we can go through and think about what the domain, range, codomain would be if they are functions. So let's kind of just take a look at these, yeah, and we'll kind of come back to this question that you have about the distinction between these two things. So for A, f of x is mapping from R to R. So this means here's our set of inputs. We're mapping to our set of outputs. So the question is, where's my poll? Is 1A a function? So these should, just be quick comments. We're not looking for formal proof. Just do you think that satisfies the condition for a function? Okay, great, thanks. Everyone got their votes in, so everybody said yes. Someone want to just share like why they thought that was a function?
Because it has a unique output. While it might not be a individual number, it would, for any individual x, it will definitely output a unique set of y's.
So, right, so that's what we want to check here. So we'd like to say for each input, is there a unique output? Does anyone have some suggestions? So, I mean, we're kind of familiar with this idea. Let me open up the chat here. Yeah, and so someone suggested something about vertical line tests. So this is a good like visual test. So when we're working with these, if we're dealing with functions from the real numbers to the real numbers, then we can graph it and check the vertical line test. This is typically, you know, how we do things in like pre-calculus or whatever when you start thinking about functions. So for example, here, that's sort of a parabola. And right, this one, though it fails the horizontal line test, that's not the condition that we need to check. We just need to make sure each input hits this graph at only one point. Okay, so that's a yes. Same question. Do you think b is a function? So here we're dealing with f of x 1 over 1 minus x. Okay, everybody is in. So here were the results. So things were a little bit more split here between yeses and nos. So this is a function here as well. It might not be as easy to graph as the first one. So maybe, you know, if we had technology, we could graph this. Does anyone want to kind of share why they thought this one was a function? Apparently I'm not able. Oh, I am able to hear people. Cool. Okay. Yes. Sorry, Christine, I cut you off.
It's kind of for the same reasons, like every input is matched to only one output.
So every input is going to one output. And, you know, when you've got something written in the form like this, right, this tells us exactly the recipe for here's a value of x, here's how you get a value of y, and that value here is going to be unique. So if we can solve this for the output y, so anytime we have this in the form y is equal to f of x, it's going to be a function, right? And the function is going to give us a set of like recipe for getting the output. So this is a function as well. Any questions about that? Yeah, so there is some questions about, very good, about like x can't be in 1, y being undefined at some points, etc. So maybe let's talk about domain, range, and codomain here. Yeah, so these are some good points here. So I don't want to erase this. This is a yes. But if we were trying to list out what the domain is here, what's the domain in A?
All real numbers.
Yeah, so this is all real numbers. This is the set of all inputs. The codomain is going to be R as well. So the codomain is always going to be this. And the domain is going to be specified here. And then the range is going to be the values that get mapped onto by this function. So in this case, we don't map to every single real number. We map to only the non-negative ones. So in this case, the range would be the set of values from 0 off to infinity. So that's kind of the difference between the range and the codomain. So the range is a subset, might be the same as the codomain. Questions? So then in B, that's right, I should be more careful. So here we have a domain which seems to be R. And so for this to be a function, then what happens is every element in the domain, every element A in the domain should get mapped, should have some image in the codomain. And that's right. People are pointing out that there's an issue here, namely f of 1 is undefined, right? It's not in the real numbers. So here I should say, technically it's no if we adjust the domain to the set of real numbers minus the number 1. Now it is would be a function. So maybe we should just amend this domain so then it would become a function. That's right. So technically this was not a function for those that said, no, you might have been thinking about that. And that's actually a really good point. So we can correct that by poking out that bad point in the domain. The range here, the codomain would just be everything in the real numbers. And the range here, we could try and graph this. I think we should be able to get everything in the real numbers here as well, if I'm thinking about this correctly. So the function here would look something like that. So we map to everything in the range, except for 0, right? Sorry. There's no way we can get a 0 out of this because the numerator is 1, right? So this corresponds to like the horizontal asymptote there. Okay, questions? Yeah, so we can map to 1 because when x is 0, we'll hit 1, but we have this horizontal asymptote at 0 that's going to give us an exclusion in the range. Okay, so how about C? So now we have a map which is going from the real numbers into the real numbers. We're going to map to 1 if the number is rational. We're going to map to 0 if the number is irrational. All right, take another 5 seconds for those that are still deciding. Okay, so we have almost a uniform distribution of responses here. So About half the people said it's not, and about half the people said it is. So let's think about it. We've got an input. Let's just see how this works. So if I want to say, where does the number 3 get mapped to? Where, according to this function, or this relation, I should say, where would 3 get mapped to?
To be 1, right? 'Cause it's a rational number.
Yeah, so 3 is rational, so it gets mapped to 1. One unique number, right? It gets mapped to the number 1, and that's it. If I wanted to say, well, like, what is Q of 0.25? That also is a rational number, so that gets sent to 1. And then we have things like Q of pi. Since that's irrational, that would go to 0. Q of square root of 2, that is irrational, that goes to 0. So we have an issue with multiple inputs going to the same output, which is fine as far as the function is concerned. What we want to be careful about is, for each input, are we getting a unique, or are we getting one output? And so for each number that I plug in, either it's rational or it's irrational. If we had numbers that were neither or both, we might have a problem. But since this splits up all of the numbers are either rational or they're irrational, numbers are going to get mapped either just to the number 1 or to the number 0. So this is a yes, since we can do this for any real number. And so here the domain, right, is going to be real numbers. The codomain is also going to be real numbers. And then the range in this case would be what?
Be 0 or 1.
Yep. So here the range is actually just a discrete set of numbers, just 2 numbers, 0 and 1. Any questions? Okay, so lastly, we'll come back to this quite a bit at the end of the class, end of the semester. I'm talking about cardinality of sets. So the cardinality of a set is how many elements are inside of that set. So for example, the cardinality of X, which we can write like this, would be 100 because this set X contains 100 things. We would say the cardinality of empty set is 0 because it contains nothing. And what we need to think about is what happens, what's a little bit more complicated is when sets have infinite number of elements, and we need to consider, are all infinities kind of created equal? And we'll see that they're not. But here we've got some finite sets, so we don't need to worry about uncountable things or infinite things. So what this map is saying is we're going to take something from the power set of X. For example, the set 1, 2, 3 is in the power set of X. And this map is saying that I'm going to map this subset to how many elements are in the set. So I should say the 3 is not significant because it's the biggest value, right? We're counting the number of elements in that set. Okay, so let me open up this one and see what you guys think. Do you think that this map is a function? Take another 5 seconds, please, to just get your best guess in, educated guess. All right, great. Everyone's got them in. So here are the results. So people thought yes, but not really sure. So there seems to be quite a bit of uncertainty. That often happens with power sets. So let's first kind of think about the domain. So in these cases, right, I mean, in this case, we don't really have a map, since this is, or a graph, I should say. Can't really plot this on like an XY coordinate system. So vertical line test is not really going to be all that useful here. But at least here, what we see is that the domain would be the power set of X, and we're excluding the empty set from that. And the codomain is the set of natural numbers. And just to remind us, the set of natural numbers would be all the positive integers. And so here, right, each subset is going to have some finite number of elements in it, right? And that's going to be unique. So for every set that I have, it's not going to get mapped to multiple outputs. It has a set number of inputs, and that's a fixed number, right? So this map is saying take a set, count how many elements are in that set, that's the output. So we have no problem here, since every set has a fixed number of elements. But let's think about what the range would look like in this case. Anybody have an idea of what this range would look like? Yeah, so that's right. So it's going to be 1 to 100, but like not the continuous spectrum of numbers between them, just a discrete set of 1, 2, 3, 4, 5. So if you think about what's the smallest element, or what's the smallest number that we can get in the range, it would be 1, since any singleton, right, has cardinality 1. And you think about, well, what's the largest possible subset that we can have? And that would be the set X itself, which has 100 elements. So actually the range here is equal to the set X itself. Meant to stop the poll there, sorry. Any questions about the notion of function, domain, codomain, range? Okay, so yeah, and we'll come back to this idea of one-to-one towards the end of the semester. Again, it's just a natural world for us to try and prove things, the world of functions, right? This is kind of our main object in mathematics. So I want to get us used to doing some proofs with functions, since we've been doing proofs with sets. And now we're going to talk about maps between sets, and we can do some proofs with those. So by definition, and so this is certainly in addition to the definitions we had on the first page, this is the kind of most important definition, say for today, which is what does it mean for a function to be one-to-one or injective? And this is now telling us that for every input, we have a unique output, right? So each output has a unique input in addition to that. So that's the added element that we have here. So another way that we could say this is each output that's in the range has a unique pre-image in the domain. In other words, it has a unique element which is mapped to it. Okay, so graphically, if we're looking at these things, the test here, vertical line test does function, horizontal line test would check for one-to-oneness. Right, I could draw a horizontal line through this, and if I hit it in, sorry, if I hit it in two different places, that means there were two inputs, x equals -1 and x equals 1, that get mapped to the same output. So if it fails the horizontal line test like this one does, it's not injective. If it passes it, then it is injective. So coming back just to these ones over here, right, this would be not injective since it fails that horizontal line test. Okay, this is injective because it passes the horizontal line test, and we just need to be careful that, right, as we get closer to the horizontal asymptote, it still passes the horizontal line test. What do you think about C? Is this one going to be injective? You guys like polls? What do you guys think about C? This is great. Thank you for your responses. This is so helpful to see what everybody is thinking. Great. So here are the results from this one in case you're curious. So we had some yeses, some nos. And so for someone that said no, this one is not injective, this one being C. And why would that one not be injective?
At like every integer, you'll be crossing the 1 point many times.
Yep. So right, we can see here that there were two numbers, 3 and 1/4, or any other integer. That's right. They all get mapped to 1. We see that these are getting mapped to the same output. So since we have multiple inputs going to the same output, where a function doesn't violate the function, but it does violate the condition for being injective. And over here, same sort of problem, which is we have, right, two different sets, the set of 1 and the set of 100, and they both get mapped to the same number, which is 1. So I'll just say that there is some connection between the cardinality of the domain and the cardinality of the range in order for us to say something about injectiveness, right? If the domain has more things than the range does, then certainly, right, multiple things in the domain are going to have to get mapped to the same thing in the range. Okay, so maybe we'll come back to this formal proof in a second, but I want to just build off of our intuition, since I think that these are ideas that you're likely to have thought about before. And so let's just kind of make sure that our intuition is there, and then we can think about how to prove these things a little bit more formally. So we'll keep playing this game, the poll game here. So for 2A, What do you guys think? Is this one injective or not injective? We already did B. Okay, so here are the results at this point. So things here are leaning towards no in part A. And so if we want to think about how I can prove that something is not injective, that's much easier, right? Because we can provide just a counterexample. So for example, in B, I can see that f of 2 is equal to 4, f of minus 2 is equal to 4. So they have the same output, but the pre-images are not equal to each other. So that violates the definition of one-to-one injective. So what's a counterexample? Someone have a counterexample for 2A to verify that this is not injective? Great. Yep. So things like 1 and minus 1. That's right. So if I take f of 1, I get the absolute value of 1, which is 1. I take f of minus 1, and take the absolute value of minus 1, which is also 1. So they have the same output. So this is telling us that here are two inputs that have the same output, but they're distinct inputs. Any questions? Okay, so let's try, what do you guys think about C? Okay, so here people were leaning towards, share it with you, leaning towards yes in this one. And someone want to kind of share their thinking about why they thought yes on this one? Yep, passes the horizontal line test. That's right. Thank you. That's what Mitchell chatted in here. So right here's graph, and every input has a unique output. Every output has a unique input. Something like D is not injective. And so in order to think about that, we need to identify kind of what are two different inputs that get mapped to the same output. I'll just get the ball rolling here. So what's one value of X which is going to get mapped to 0?
0.
Yeah, okay, so that's one of them. And what's another one that would get mapped to 0 as well? If you're not kind of seeing that right away, right, we could factor this, yep, and then we can see that 1 would be another one. And so would minus 1 for that matter. And so this fails the one-to-one test for that reason. Okay, so let's see where we're at here. So maybe let's try and move over towards proving things a little bit more formally. So it seems like the intuition is good. It's coming there. So for these, I'll put up the solutions, but sorry. Okay, and then this last one is also not a function. No, it's a function. It's injective, right? Since each person has a unique set of initials, but there could be two people that have the same initials. I don't know if I think we have a unique set here as far as I can see. But yeah, I'm usually a pretty common one since A and S are common first and last initials. Yeah, but certainly I know Alan Spiegler is out there because he steals the email addresses and Twitter and all these things before I get to it. So me and Alan Spiegler, we are not related, but we've interacted with each other because people send him stuff all the time that's supposed to come to me. Okay, so yeah, if you're kind of curious about proving these things a little bit more carefully, I'll put up explanations for those. But I want to have some time to start to think about more formal proofs or disproofs of these statements. So maybe let's do this one, which is injective. This one being G. And let me just back up and explain what this floor function does. There's also a corresponding ceiling function that works kind of similarly, but this is just like, let's ignore the decimal point. So this is not the same as rounding, because over here, we would take something like 4.9 and it would get mapped to 4, right? So we're just ignoring whatever comes after the decimal here. So this is not going to be a function, just to back up for a second, because we have things like f of 4.9, f of 4.1, they both go to 4. So that violates this idea of being one-to-one, I should say. I don't see why this would not be a function, sorry. This is not injective. But it is a function, sorry. Yeah, so this is exactly like a step function, that's right. So we would have everything here would go from here to here, and then we hit 1, suddenly we bounce up, and then we bounce up again. So it does pass the horizontal line test, but it very badly fails the, passes the vertical line test, but fails the horizontal line test. So let's take a look at G, and the difference here is the domain that we've defined here, right? So now we're only considering integers. So now we just get a bunch of dots that are going up. So let's prove this, see how we could do this. And so definition of injective, just to come all the way back up to that. It is right here. So if we want to prove this is injective, then what we need to show is this. Okay, so this is a conditional statement. So I'm proving these things same way that we can prove a conditional statement. So one way that we could do this with direct proof would be, and this is kind of summarized, we skipped over that page, but by supposing P and then trying to get to Q, right? The kind of first way that we did these proofs. If we were going to do this by contrapositive, let me get this poll out of the way. What would the first sentence of that proof be?
F of x equals f of y.
Yeah, so here we start with not Q. That's right. So we're going to suppose Q was that they're not equal to each other. So not Q is, let's suppose we have two different inputs, X and Y, that have the same output. Then what would the last step hopefully be? What would we want to show?
X equals y.
Yeah, so then we want to show that in fact X and Y are not distinct. They have to, the only way the outputs are equal to each other is if we have the same input. And if we were doing this by proof by contradiction, remember the goal is a little bit vague here. We're just trying to get some contradiction, but what would we want to suppose to prove this conditional statement using contradiction? So we would assume that P is true. So we assume the hypothesis, which is X is not equal to Y. And remember, when we negate, which is what we want to start with, a conditional statement, we get an and statement. That's right. So we're going to say, suppose X is not equal to Y. So we have two different inputs, and they give us the same output. So this is exactly what it means to not be injective. So we're going to assume that this thing is not injective and then reach some contradiction. So we can apply all three of these proof techniques to injective proofs. And I'll just say this is kind of a situation where oftentimes contrapositive is the nicest way to do these because it's a lot easier to start by assuming things are equal to each other. That's a more defined thing rather than saying two things are not equal to each other. But oftentimes you could take one and see how it goes and then recreate it in a direct way. Okay, so let's prove this over here. okay, where we're working with this function r, which is mapping from the integers, not all real numbers, into the integers. And that's why we have, that's what's going to make this injective. So I'm going to do this by contrapositive. So I'm going to note that initially so that my first line of the proof makes sense. So our function here is r. So let's suppose we have some r maps some number x, some integer x to the same place it maps integer y. And here it might make sense to here identify it that these are integers, right? X and y are integers, and that's going to be important here because if they're real numbers, we wouldn't necessarily be able to prove this. So this implies the floor of x is equal to the floor of y. That's what these sorts of things look like. I think you probably could do this by contradiction, and that might be a good way to do it as well, actually. I think that would be a pretty quick one if you think about it, right? If I have two integers that are different from each other, there's no way that they could have the same floor, for example. So I think you could get a pretty good contradiction out of that one too. Okay, any questions? Okay, so let me try another one. Try this one. And then I want to give you guys a chance to get some practice in on one yourselves. So now these are a little bit general. So now I don't actually have like a full-on proof, a full-on well-defined function. So here we're actually not necessarily like proving that something is injective, but rather we're going to kind of, that's part of the hypothesis here. So I'm going to try to prove this directly, which means I'm going to suppose indeed that the hypothesis is true. This function f is injective. So any thoughts about what we could do next? Yeah, so let's start with the definition, right? That's always a good place to go, regardless of what we're working with. So we've got this injective thing. So this would tell us so if I have two things, X and Y, and again, I should define what these things are before I say something. Okay, that's the definition of injective. And right, that would kind of be the thing that we would want to be able to show before we can then claim that H is injective. So any thoughts about how we can get there?
Could you like add C to both sides?
Yeah, or we can start by, well, this is how H is defined, right? So let's go ahead and see. We know that X is not equal to Y, right? That was what we kind of assumed up here. So we kind of have this assumption already. And so what we need to show is that by assuming this, we're going to get this. And since we have the function H of X defined, yeah, and so maybe we could actually I like that idea of just like let's add C to both sides. Right? Since if two things are not equal, then when we do the same operation, then they're still not going to be equal. And f of x plus c is exactly h of x. F of y plus c is exactly h of y. And that is why those two things are not equal to each other. So just to kind of connect this in a slightly more continuous way, right? Thus we see if x is not equal to y, then it has to follow that h of x is not equal to h of y, then by definition, h is injective. So we kind of did one proof, just like here's a function, show that it is injective. And here's a proof that involves the definition of injective in it. Any questions? Yep. Okay. Okay, so in B, so this is actually not a true statement. And so if we want to prove it's not a true statement, then we need to provide a counter example. So can you think of a function f, which is 1-to-1, and a function g, which is 1-to-1, but when we add them together, we get something which is not 1-to-1.
I think the example from earlier
Yeah, I was going to
was
say.
x cubed.
That's right.
Yeah,
Here's a
and then
hint.
negative x.
That's right. For something that could work, which is exactly this function over here, which we commented was not injective because we have multiple x-intercepts. But this is made up by adding, in this case, subtracting two functions that would be 1-to-1. That's right. So let's say that over here. Okay, so adding, subtracting injective functions doesn't necessarily result in another injective function. Adding a constant does. Any questions? Okay, so I want to kind of give you guys a chance to try one proof out today, and my hint for the one that we skipped over 3. So if you should happen in your group to get through C quickly, then you can come back here and think about how you can use A and C from below over here. But yeah, so let's try and prove this one. And so what we're trying to show, this is an if-then. So that's like our P over here. And this is like our Q. We want to show that. And again, so here you've got the definition for strictly increasing. So so you know where to go if you suppose that it's strictly increasing. Any questions before I set up the rooms? All right, welcome back, everyone. Good, so let's take a look at what you guys came up with on this one. And I think what I want to be clear about is how we define what it means to be strictly increasing. I don't know if I was clear in the statement of the problem. That clearly is important if we're going to try and use this definition. So what it means to be strictly increasing tells us that if x is less than y, then it has to follow that f of x is less than f of y. I think the way I phrased it was like, if f of x is less than f of y when x is less than y, which is maybe not typically how we state conditions. But here we're going to assume x is less than y, and therefore that's going to imply f of x is less than f of y. So let's kind of think about, if we're doing this directly, we're going to start with that, and then we're going to try and show that f is injective. just to remind us what that definition looks like is we want to say this. So let's kind of start by supposing we have two real numbers that are not equal to each other. Right, then if we've got this, if they're not equal to each other, one of them has to be less than the other, right? So without losing anything in this proof, let's just suppose x is the smaller one, y is the bigger one. And this term here means if instead we had y being less than x, the proof would follow the same exact way. So let's not get too worried about which is smaller than the other. And so if x is less than y, since we know that f is strictly increasing, this tells us that f of x, therefore it has to be less than f of y, which then tells us they're not equal to each other. And then f is injective. Any questions? So we're out of time. Kind of skipped over this one over here, so I can fill in this part now that we've proven a couple of things in question 4, and I'll also kind of go back over here and fill in some of the details. So the ones that are not injective, I can give a counterexample. This one we kind of did prove a little bit more formally. We can take a look at like what a formal proof of this would look like as well, since just drawing the picture wouldn't be enough for a formal proof. So I might suggest that you try and practice proving this. And I'll put up a solution if you want to check it with that. But you also have plenty of injective problems on the homework, so you can start with those too. Okay, well, if you have any questions, you're welcome to stick around. Lindsay's got office hours today, right, from 1 to 2, if I'm remembering correctly. And homework is due tonight. I've got office hours tomorrow if you have some additional questions about that. Otherwise, have a nice afternoon, everyone, and I'll see you on Wednesday.